Back to the shirts and pants example from the starter. So I just want to represent it slightly differently. Remember, we had 5 shirts, 5 different shirts, I should say. Another keyword that we might want to know is distinct. 5 distinct. So distinct means we can tell the difference between them. Can tell the difference between them. Could probably add that to the key vocabulary, actually. In fact, let me do that. Distinct. And distinct means can tell apart, can tell the difference between them. So just for example, generally typed letters are not distinct. This P and this P are not distinct. Not distinct. I cannot tell the difference between them. They both just look like a P to me. But different letters, you can tell the difference. So for example, I and J or A and B are distinct. Humans or animals are generally distinct. You can tell the difference between 2 cats, even though they're both cats. You can tell the difference between 2 humans, even though they're both humans. Anyway, back to this. We have 5 distinct shirts and 3 distinct pants. And we want to find the number of combinations of shirts and pants. And I love this diagram because it says you can think of each choice of shirt as a pathway, as a direction you can go, maybe in life. I know it's a little silly because it's just putting on a shirt, but hey, this is a choice that can be made. So this is like a path of life. And then for each choice of pants, this is a different path after that. And that gives a total of 15 possible journeys. For example, going down this path here, choosing the first shirt, and then choosing this pair of pants. That's one of our possible journeys. The journeys are here, at the end here. So going down this path and then this path results in this shirt and these pants. And so yeah, in total we got 1, 2, 3, 4, 5, 6. You get the idea, all the way up to 15. And of course it has to be 1, 2, 3, 4, 5 times 1, 2, 3. So that's using the product principle. 5 times 3. You've got 5 paths to go down at first, and then for each of those 5 paths, you have another 3 paths that you can go down. That gives you a total of 15 possible journeys. Okay, let's do an example here. It says, Alfred is caught by a surprise test, which consists of 4 true or false questions. Illustrate on a tree diagram, or path diagram, you could probably call it if you look at the previous example, the possible ways in which he can answer all the questions purely by guesswork, hence deduce the number of possible answers for a 10-question test. Okay, let's go ahead and do our path diagram for the first bit. So question number 1, he can answer true or he can answer false. And then after he's answered true for question 1, so this is question 1, he can then move on to question 2, where he can answer true or false again. True, false, true, false. So that would be question 2. And then for question 3, the same again. True, false, true, false, true, false, true, false. True, 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 false. You get the idea. So that's for question 3. And then for question 4, the same again. One last layer. So that is question 4. So all of the paths down this, what's called a tree diagram here, they represent the different options he can take. For example, true, and then false, and then false, and then true. That's one possible option. True, false, false, true. Another possible choice is true, 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 and then true. That would be this path here. So the point is that the ends of all these paths on layer 4, these represent the well, the ends of the pathways, of all the different pathways that we can take. And we can see there are 1, 2, 3, 4, all the way up to 15, 16 of them. And even without drawing this diagram, we can pretty quickly see that it's 16, because when let me just go through this example again. True, 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 true. If I'm going to write it out, it looks like this. T, 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 T. So those are his answers to questions 1, 2, 3, and 4. But in general, we've got 1, 2, 3, 4 spaces. 1, 2, 3, 4. And in each space, we can put true or false. True or false. T or 5. T or F. True or false. True or false. True or false. For each of the 2 choices for position number 1, we have 2 choices for position number 2. And for each of those 2 times 2 choices for positions 1 and 2, we have another 2 choices for position number 3. And for each of those 2 times 2 times 2 choices for positions 1, 2, and 3, we have another 2 choices for our final position. So that's going to give us 2 to the power of 4 equals 16 different choices of answers to these 4 true or false questions in total. And then it says, hence deduce the number of possible answers for a 10-question test, assuming true or false questions still. Well, it's the exact same idea, except this time instead of 4 positions, we have 10. And in each of these 10 positions, we can put a T or an F for true or false. And so that's going to give us a total of 2 times 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 2. I think I got 10 of them. But yeah, it's much easier to just write 2 to the power of 10. And that is 1024. So just one more statement of the product principle. If you have n different first paths you could travel down, and at the end of each of these paths there are m different second paths you could travel down, you could make n times m different journeys in total down 2 paths. How about if at the end of the m second paths there are p third paths? So we've got, just to make it clear what it's saying here, we've got 1, 2, 3, 4, we've got, it doesn't matter how many there are, but there are n different first paths we could travel down. So there are n of these. And then at the end of each of these there are, I don't know, m of these. So m of these. So we know that there are a total of n times m different journeys down the first 2 paths. N times m journeys down red and green paths. The idea, of course, is that you can only go down and then down. Like you have to keep going down. You can't like go back up or something. Then that's a whole bunch of other different journeys. So assuming you can only go down, we have n times m different ways to do that in total. And then it says at the bottom here, how about if at the end of the m second paths there are p third paths? So there's p paths here. I'm kind of running out of room, but hopefully you get the idea. Feel like I'm gonna get called out on my picture here, but yeah, there are p of these at the end of each of the branches, so that gives us a total of n times m times p different journeys. Sorry, I should make it clear when I said m of these and p of these. It's m of these at the end of each of the red branches, and there are p of these at the end of each of the green branches. So m of these at the end of each red path. And there are p of these at the end of each green path.